Hello, my name is Yan Mengyu. My student ID is CST25090551. Our group topic is determining the volume of water in a reservoir. In this presentation, we will show how calculus can be applied to solve a real-world engineering problem. And I will first introduce the background of our project and explain why this problem requires calculus. Reservoirs are an important part of modern water resource systems. They provide clean water for cities, support agricultural irrigation, generate hydroelectric power, and help reduce flood risks. To manage these functions effectively, engineers need to know one key piece of information: how much water a reservoir can store. Therefore, estimating reservoir volume is not only a mathematical problem, but also an important engineering task that supports water resource planning and management. However, calculating the volume of a real reservoir is much more difficult than calculating the volume of a regular object. Unlike a rectangular tank, a real reservoir does not have a regular shape. Its boundary is irregular. The bottom is uneven, and the water depth changes continuously from one location to another. Because of these characteristics, simple geometric formulas cannot accurately determine the reservoir volume. This means we need a different mathematical approach to solve the problem. This is where calculus becomes useful. Instead of treating the reservoir as one large object, we divide it into many tiny regions. Within each small region, the water depth can be considered approximately constant. The volume of each small part can then be estimated as the water depth multiplied by the small area. Finally, by adding all these small volumes together, we obtain the total volume of the reservoir. This idea is the foundation of the double integral, which will be used in our mathematical model. Now, I will hand over to my teammate, who will explain how we construct the mathematical model of the reservoir.
Hello, doctor. My name is Wang Yubo, and my student ID is TCM240906. The purpose of this section is to convert the real reservoir problem into a mathematical model that can be calculated. In real life, a reservoir usually have an irregular boundary and an uneven bottom surface. Because of this, we cannot directly use simple volume formulas, such as the volume of cuboid. Therefore, we make reasonable assumptions and simplify the real situation into mathematical model. This model will become the foundation for the later calculation. First, we assume that the reservoir is a typical valley reservoir. This means the reservoir is located between two mountain slopes. The center part is deeper, while the area near the edge are shallow. This assumption matches many real reservoirs and helps us describe the depths more clearly. Second, although the real reservoir boundary may be irregular, we approximate the horizontal base as a circular region. The circular region is written as the first function. This assumption makes the boundary easily to describe and also allow us to use polar coordination later. Next, we define the depth function of the reservoir. Since the reservoir is deeper in the center and shallow near the boundary, we use quadratic function, the h function. In this model, each function represents the depth and at the point xy. When x equals 0 and y equals 0, the depth is 8. So the maximum depth is 8 units at the center. As x or y moves away from 0, the depth decreases. Also, the coefficient of y score is 0.12. which is larger than the coefficient of x score, which is 0.04. This means the depth decreases faster in the y direction than in the x direction. So, the model shows that the reservoir bottom is not perfectly symmetric, which makes it close to a real landform. After defining the region and the depth function, we can build the volume model, the first one. This double integral means that we divide the reservoir base into many small arrow elements, called it dA. Each small arrow has a depth of function h, so each small volume is approximate the h function dA. By adding all the small volume together, we get the totally reservoir volume. After substituting the depth function, the model becomes the second one. Because the base region is circular, we can use polar coordinated, the third one. So the final volume model can be written as the last one. So in conclusion, my part changed a complex real reservoir into a clear mathematical model. We assume it is a Woolley reservoir, simplify the base as a circular region, and define a depth function, and finally build the double integral model for volume. This prepares the project for the next part. So this is all my parts. Thank you.
Hello everyone, I'm Yang Yunan, CST 2509053. Now before the practical application, that we first answer the question why double and triple integral can be used to calculate the volume of the reservoir. Because the depth of the bottom of the reservoir changes with the position, it cannot be calculated directly using the bottom area times height. For double integral, the water depth varies across the base. By integrating the depth function over the entire base area, the volumes of infinitely many small vertical columns are summed together, giving the total volume of water. And by triple integral, because the water occupies a three-dimensional ring, by integrating the constant function 1 over the entire volume of the reservoir, all infinitesimal volume elements are added together to obtain the total water volume. And now it's our practical application. The question is, assuming that the bottom of the reservoir is a circle with a radius of 7 meters, and the water depth at any point is approximated by this function, and what is the maximum storage capacity of the reservoir? All the variables are measured in meters. For this, we can use two ways to solve this. First one, we can use double integral, and second, we can use triple integral. First, by using double integral, because we know that the base of this reservoir is a circle, so we can use polar coordinates to simplify the calculation. We substitute x equals to r cosine theta, y equals to r sine theta. And we know that it's a circle with radius of 7 meters, so it's their range. And based on the coordinate transformation, we can know that dA equals to r dr d theta. And so we got this expression, and then we just integrate it respective to r, and we got this, and then we just integrate it respective to theta, terms by terms, and we get this in this final result, 929.8 cubic meters, which means that the maximum storage capacity of this reservoir is 929.8 cubic meter. And now we can use triple integral to solve this problem. Different from double integral, triple integral introduce an additional variable z to represent the vertical dimension. So it's a range. And same as using double integral, we use the polar coordinates to simplify the calculation, and it's their range. And based on the coordinate transformation, dv equals to r dz dr d theta. So first, based on this, we integrate respective to z, and we integrate respective to r, and we integrate respective to theta terms by terms, and finally we get this answer, 929.8 cubic meters, which is the same as using double integral. Thank you.
Hello everyone, I'm Yu Zhijie, CST2509057. Now I will explain the interpretation of our results. After calculating the reservoir volume using both the double integral and the triple integral, we obtained the same answer. This shows that our model is both consistent and reliable. Although the two methods use different approaches, they calculate the same physical quantity, which is the total volume of water stored in the reservoir. The calculated volume represents the maximum storage capacity of the reservoir under our assumptions. This information is very useful in engineering because it helps estimate how much water can be stored and managed. The model also has many practical applications. It can support water supply management, irrigation planning, hydroelectric power generation, and flood control. Therefore, calculus is not only a mathematical theory but also an important engineering tool for solving real-world problems. Next, let's look at the practical implications and the limitations of our model. One important application is helping engineers estimate available water resources and make better decisions for reservoir operation. It can also improve flood management and support long-term planning of water resources. However, our model has several limitations. First, we simplified the reservoir boundary into a circular shape, while real reservoirs usually have irregular boundaries. Second, the water depth is represented by a simple mathematical function, which cannot fully describe the actual terrain. In addition, our model does not consider sediment accumulation, seasonal rainfall, evaporation, or changing water levels. These environmental factors may affect the actual storage capacity. Therefore, this model is mainly suitable for demonstrating the application of calculus rather than proving an exact engineering design. Finally, I would like to discuss some possible improvements. In future studies, engineers can use GIS technology or drone surveys to obtain more accurate reservoir boundaries and terrain data. A more realistic depth function can then be developed based on actual field measurements. We can also include seasonal water level changes, sediment accumulation, and other environmental factors to improve the accuracy of the model. For more complex reservoir shapes, numerical integration methods can also be applied. In conclusion, this project demonstrates that multiple integrals provide an effective model method for estimating reservoir volume. Mathematical modeling allows us to simplify complex engineering problems into solvable mathematical models. This project also shows that calculus has important application in civil engineering, hydrology, and water resource management. It demonstrates how mathematical knowledge can support practical engineering decisions. These are our references. Thank you very much for listening.